So we'll have a quick detour again. We'll talk about Markov property. Markov property basically allows us to have a very compact form for joint distribution. You remember, so let's say you have a joint distribution over n variables, xn through x1, and you can use this telescopic rule. So it's a conditional xn on everything else, x1 through xn minus 1, times the joint over x1 xn minus 1, and then you can take this joint over x1 through xn minus 1 and again expand it using the conditional. So you have conditional xn everything else times conditional xn minus 1 xn minus 2 x1 times the joint x n minus 2 x1, and you can continue doing that before you basically get xn on anything else, xn minus 1 x1 times x1 xn minus 1 conditional on anything before xn minus 1, so xn minus 2 all the way to x1, and then at the end you'll have x2 conditional on x1 times marginal over x1. So that's a telescopic rule or telescopic formula that allows you basically to write down the joint distribution. And Markov property allows us a much more compact form of writing this down. Markov property says that distribution over xn conditional on the rest of the variables xn minus 1 through xn actually equals to xn times xn minus 1. So we have a very compact and very short formula for writing this one. So on the Markov assumption, the joint will be like this. You have xn given xn minus 1 times the prior probability of xn minus 1 given x, and then again given the Markov property that equals to xn minus 1 given, sorry, it's xn conditional xn minus 1 and then xn minus 1 conditional on x minus 2. So remember, it doesn't depend on anything else, times, and you can continue. This is going to be x2 conditional on x1 and then times x1. So Markov property just allows us to conveniently define those joint distributions. Essentially what happens here, only the current history matters when determining the probabilities. In order for you to calculate distribution over xn, you only need to know xn minus 1, and conditional on that you have what is called conditional independence. Conditionally, xn is independent of xn minus 2 through x1. Okay, so let's see a quick example of this Markov property. We're going to look at S&P 500 daily ups and downs. So you have data here from 97 to 2007, 10 years worth of data. And what you see here is a daily return. Each dot is a daily return. So you have some outliers here. You have some days when S&P 500 went up 5% and outliers on the opposite side of the zero. So you have days when S&P had huge downs, and we're going to look at this data, and we will try to see whether the market is actually Markov or not Markov, and we will build the Markov model. And let's say that you have a stock market returns on the 4 consecutive days, x1 through x4, and let's just empirically calculate the conditional distributions. So let's look at the marginal probability of market going down on any given day is 47% and going up on any given day is 52%. Well, we kind of know that when you try to invest your money, investing into markets usually on average in the long run is a good idea, and one of the reasons it's a good idea because market is more likely to be up than down, and in the long run you expect positive returns on your investments. But let's look at the conditional one. So let's look at the conditional of market, what happens on day two given what we know on the day before. And so we'll have up, 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 down, down, up, and down, down. And so when market was down on the previous day, 51%, almost 52% is going to be down today. And with the rest of the probability, 48% is going to be up. And conditional on the fact that market is up, only 43% chance it's going to be down, and 56% it's going to be up. So it looks like market is not so there is temporal dependence in the market. So what happens on the previous day can tell us something about what happens on the next day. So there are some at least local trends on the market. And what happens if we look at the two previous days? So if you have two down days, then you actually have third day 50%. So it's almost 50-50. Now the trend seems to be disappearing. And then if you have down up, then most likely it's actually going to be up. And if you have up, down, then most likely it's going to be down again. So if you have up, then down after that, then most likely we'll have another down after that. And up, up is most likely to follow with up day. So here looks like the the relationship is stronger compared to the two down, down days. And so, and then we can write distribution probability of x2 and x3 given x1, and this is joint and marginal and conditional probability at the same time, because joint because you have x2 and x3 two random variables, marginal because it ignores x4, so you have to integrate out x4, and conditional because you condition on x1. Okay, so let's look at the joint probability of up, up, down, and it's probability that market is up on the first day times the probability that market is up on the second day, given that on the first day it was up, and the probability of market being down on the third day, given that it was up the 2 days before. So under this assumption, we have those probabilities. And if we ignore the previous history, if we say there is no really temporal dependence, so then up, and down is just going to be using the marginal, so probability of up 52%, another up 52%, and then 47%. So slightly different, and actually this term is slightly different. So under the independence, looks like the probability of up, and down is slightly higher compared to the probability of up, and down under the Markov dependence assumption.